Oh, welcome to part B of chapter 10. In part B, I'll cover section 10.5, covalent bonding and Lewis structure, electronegativity, define the bond polarity, and in 10.7, we look at the Lewis, how to draw the Lewis structure for molecules and polyatomic ions. In 10.5, we will go over the covalent bonding Lewis structures. Lewis structure provide us with a simple, useful model for chemical bonding. In Lewis structure, when an element or an atom of an element form a covalent bond, they either end with 8 electrons, which is called the octet rule, or duet. For example, in a hydrogen gas, it is H with a line which represent a covalent bond with another hydrogen. The sharing of electron, if say this is a hydrogen with one valence electron and another hydrogen with one valence electrons, when they form hydrogen gas, you'll see that the sharing of electrons. This is the covalent bond, which is called duet, meaning that each hydrogen has 2 electrons. For octet rule, all right, when atoms form chemical bond, they end up with 8 electrons in their valence shell. We call this the octet rule. E.g., ICl, okay, the dot symbol for hydrogen or iodide is in group 7. So 1, 2, 3, 4, 5, 6, 7. Let's say we have chlorine here. 1, 2, 3, 4, 5, 6, 7. Each one of them has a 7. So this will form an octet rule with Cl1, 2. Remember, you pair them up. And the iodine here, I will also have these 2 paired up. The octet rule, if you look at the iodine and chlorine, they form chemical or covalent bond with each one of them having 8. 1, 2, 3, 4. 1, 2, 3, 4. We call this octet rule. 8 electrons in their valence shell, except for hydrogen, as I indicated in the previous slide, that it ends up only with 2. The sharing of electrons, this is the shared electrons. Here we have shared electrons. A shared pair of electrons, you see here, pair means 2 electrons. We have 2 electrons here. For hydrogens, we have 2 electrons here. We call this covalent bond. We call it covalent bond. We're going to talk about more covalent bond as we go along. Now, there are 2 types of electron or 2 categories of electrons in a covalent bond. We have what we call bonding pairs and non-bonding pairs. In this molecule, these are the non-bonding. So if I write here this, and that, they are called non-bonding pairs. And here we have what we call these 2 right here, bonding pairs. So whatever is just hanging out doesn't form a bond, we call non-bonding pairs. Sometimes we call those lone pairs. Atoms called lone pairs, also known non-bonding pairs. So for water molecule, H dash dash, you can see clearly that they are non-bonding pairs. These two right here and this one, these are non-bonding. You do not participate in formation of a chemical bond, non-bonding pairs. And here we have bonding pair. So there are 2 electrons in every line. This means one line is a single bond, which is 2 electrons, 2 electron a pair. So non-bonding, you see this, you can see clearly here, a line represent 2 or is represented 2 bonding pairs to form a bond. But these 2 here, these are non-bonding or lone pair. Sometimes we call these lone pairs. In a quiz, probably you see that how many non-bonding pairs? 1, 2. There are 2 non-bonding pairs. Bonding pairs here we have 2 for H2O. So remember, there are 2 types of electrons in a covalent or in a molecule when you go to Lewis structure. Now let's shift gears to types of covalent bonds. So here, types of covalent bond or bonds. There is a single bond which is represented by with the 2 electrons. There is the double bond which is represented by 2 lines, and we have 4 electrons. And then here, triple bond, which is 3 lines, and these have 6 electrons. You need to remember the number of electrons, number of pairs for single, double, and triple bond. Here we have single bond, and it's represented only by one line. When 2 atoms share 1 pair, pair has 2. We call this a single covalent bond, consists of 2 electrons. All right, duet. So for we don't look at the lone pairs here, we look at it. Duet means 2 electrons for hydrogen, oxygen. Octet rule means it has 8 electrons. In the valence shell, 1, 2, 3, 4. We call this the octet rule. Remember the octet rule. And then the double bonds means 2 lines. We'll see later on how to generate the double bond or single bond. But for now, remember 2 lines represent a double bond. When 2 atoms share 2 pairs, it means 4 electrons, 4 electrons. And each one of them ends up with 8 valence electrons, the octet rule. And lastly, the triple bond, 6 electrons, 3 lines. These are the 3 pairs of electrons between nitrogen. Still 6 electrons, 1, 2, 3, consists of or constitute the triple bond. Please remember to draw a parallel between single, double, and triple bond. As we move forward, we'll see that later on. Like previous section, covalent bonding model versus reality. Lewis model implies that some combinations should be stable, whereas others should not, because this stable combination results in octet rule. In other words, elements or atoms end up with 8 to be stable except for hydrogen, of course. Please read more on covalent bonding in the reality versus the Lewis model. Prediction of molecular model by Lewis. This is hydrogen predicting that this is unstable. If you look at how many hydrogen electrons are on oxygen in hydrogen, this explains why some molecules or polyatomic ions are unstable. I just want to go fast to the electronegativity, section 10.6. To start off with electronegativity and cone polarity, let's define electronegativity. You should be able to define this electronegativity. This is the ability of an atom to attract electrons or towards its in a covalent bond. This is the definition of electronegativity. It is a trend on the periodic table. So at the outset, what is electronegativity? Electronegativity is the ability of an atom to attract a shared electron in the covalent bonds toward itself, right? The unequal sharing of electrons leads to what we call polar covalent bond. Polar covalent bond as a result of one element pulling electrons toward itself. Now, electronegativity, trend, or even though we're gonna come back to this, but let's see, trend on periodic table. Trend on the periodic table as you go, it increase as you go down or decrease. This is the trend on electronegativity. This is increase as you go from left to right on the periodic table. As you go down, it decreases. Francium is the least electronegative. Fluorine is the most electronegative on the periodic table. And when we talk about the polar covalent bond here, let's say we have a molecule such as hydrogen fluoride. Fluorine is the most electronegative, so it will share the electrons. Even though we have it like that, the sharing of electrons is not equal. So if that is the case, electrons spend more time in, or fluorine pulls the electrons because it is most electronegative. You see these, the electrons are closer to fluorine. And if we have this this structure, we indicate this as partially positive because it is electron poor region of the molecule, partially negative electrons rich portion of the molecule. We say that this bond is polar bond because there is equal sharing of electron polarity. How do you know that which region has more electrons? It's based on the trend on the periodic table. You have to see where the elements are. The end that is electron division gets a partially positive. This is what I just indicated here with the partial positive, partial negative in polar covalent, and I should say covalent here so that you know exactly that it's a covalent bond, polar covalent bond. Others or some others use electrostatic potential map, which is the color coding. The electron for region of the molecule is indicated by the blue color, red for electron-rich portion of the molecule in electrostatic potential mass, but nevertheless, partially positive, partially negative for polar. We say this is a polar covalent bond and the molecule is polar. We're going to talk about that. So bond polarity is resolved because of an equal sharing of electrons. Bonds are classified as covalent if the amount of electron transfer is insufficient for the material to display classic properties of ionic. That means it's not completely transferred. In other words, even though you see here, it's not completely transferred to fluorine as in ionic compound. An equal sharing produces a dipole bond. Bond is classified as polar covalent. So you may see in the quiz or in Alex's assignment that which one of the following has a polar bond. You should be well-rounded in electronegativity, which I just explained. I divine, show you how to come to a conclusion as to which element is more electronegative in order to conclude that it's a polar covalent bond. It has to do with the position on the periodic table. I've defined electronegativity. You should be able to define is the ability of an atom to attract bonding electron towards itself. It's called electronegativity. This is the trend. From left to right, it increases. Fluorine is the most electronegative. All right, francium is the least electronegative. This is what I indicated in the trend. I like to use some illustration. I like to visually look at. So this is the most, this is the least. On the PowerPoint slide, it's mentioned here, all right? The larger the difference in electronegativity, the more polar the bond is. So you can know where they are on the periodic table. If we are given two elements, look at the position on the periodic table. Oh, well, no one will ask you to memorize the numbers you see here for fluorine. It has an electronegativity value of 4 and francium electronegativity value for 0.7. Down the line, we will make use of these numbers to classify a bond as polar covalent, non-polar, or ionic, but you'll be given if need be, all right? Let's see, conceptual question. If you are asked, arrange the following elements on the periodic table, see which one is the, according to decreasing or increasing electronegativity. What you need to do is you circle, you eyeball on the periodic table. I'll give you in the quiz, maybe taking exam. I'll ask you to I'll give you the periodic table. Yours is to write and see where they are. If I look on the periodic table, you have to see where they are. Sodium, phosphorus, this is nitrogen, and this is aluminum. The challenge is if you don't know the names, if you don't know where to look or what to look for in the periodic table, it will be very difficult for you to make a conclusion. So if I look at this, the correct answer is a decreasing nitrogen is greater. This means greater, all right? In mass, this implies greater. You forget, this means less than, and I'll read this as nitrogen is more electronegative than phosphorus, which turns to be more electronegative than aluminum, and least more electronegative than sodium. Remember, sodium is on the far left on the periodic table, so it's going to be the least. This will be at the top, far right on the periodic table. give me this pattern. You can use elimination method and come up to a conclusion. So the correct answer is A for this. Now, list which one of the following element has the lowest electronegative, and again, you need to circle on the periodic table. The correct answer for this is D. All right, look at where it is. If I look on the periodic table, nitrogen is on this side, followed by silicon is on the gonna be in this pattern, and cadmium. This is cadmium on the periodic table. Remember, on the periodic table, this is how it is, increase, and then this is decrease in electronegativity, En for electronegativity, and the correct answer here is cadmium, Cd. Please practice more. Which of the following molecules contain the most polar? All right, the most polar means the one with the shared electrons being pulled towards one atom in the molecules given here. As I said, fluorine is the most electronegative on the periodic table, which means it has high power to pull electrons toward itself. And it turns out that A has the most polar, You can see that tellurium, the carbon tetrachloride, they are not as such. So let's see, electronegativity difference and the type of bond. As I say, those values, the values I gave you earlier on here, these values you see, not that one, is right here. The values you see here will be given for each element to use to determine whether the bond here is covalent, pure covalent, non-polar, polar covalent, or ionic. For you to come to a conclusion, you have to find change in electronegativity. I'll look at the second element, which is the most electronegative. You subtract, for example, electronegativity value for chlorine, let's say HCl, electronegativity values, if we go to the table here, which I'll expect or I'll give you, chlorine is 3.0. So this is 3.0, and hydrogen is 2.1. So if I minimize this is what I have on the values. You'll be given that. And if I want to find whether it is polar or non-polar for HCl here, it will be change in electronegativity is given by 3.0 minus 2.1. This is 9, all right, 0.9. And if you look at this domain, 0.4 to 1. We say polar covalent. So the bond here, we say this is the polar covalent. If I have chlorine plus, this implies it's ClCl, and electronegativity value is 3.0, 3.0. Change in electronegativity is given by 3.0 minus 3.0. This is 0, and the bond here is said to be we say this is covalent. Just typical covalent, and if it's something greater than 2, larger than 2.0, ionic bond. So that's how you use the second element minus first give you the region where you need to look at these domains. So if I'll commit my memory to domains, I'll not give you these values in the exam, but you need to know the domain 0 to 0 0.4, 0 0.4 to 4 to 4, 0 0.4 to 2.0. This is polar covalent, and anything greater than 2.0 is ionic. It's the same thing. It's just only that we are using a value. So if we share this could be hydrogen gas, this could be oxygen gas, and so forth. Unequal sharing, polar covalent. Complete transfer, anything greater than 2.0, 3.0 is complete transfer. This is ionic bond, ionic bond. Given the electronegativities below for each element, which covalent single bond is the most polar? You need to do the difference, and if you like in the values, what turns out to be the most polar in this case is or see if you do the calculation for hydrogen, okay, a change, this means change in electronegativity for A, you should have 0.4, B, this is 0.9, C, this is 1.4, D, this is 1, and E, this is 0.5. The question is the most polar. This will be C. If you find the electronegativity or change in electronegativity, you subtract, find the difference given this. So in exam, you'll also see the same, not exactly, but other elements as well, given electronegativity values for elements on the periodic table, you should be able to determine the change in electronegativity and either classify the bond as covalent, polar covalent, or ionic. The most important thing is to know the domain. 0 to 0.4 covalent, 0.4 to 2.0 polar covalent, and anything greater than 2 is ionic bond. Now, the transfer of electrons or unequal sharing of electrons is indicated by what we call dipole moment, represented by the Greek symbol nu. This nu is a measure of bond polarity. To what extent is, or to what extent are electrons transferred from one element to the other element? This is directly proportional to the charge, all right, times the radius, and it is measured in dpi. This dipole moment is measured in dpi. This is the charge. Dipole moment is measured by Q. This is the charge times R. This is the radius in meters, radius of the atom in meters. It's measured, the unit is, gonna look at the device. So this is how to determine to what degree the electrons are shifted towards a more electronegative element in a molecule. Generally, dipole moment, the more electrons, two atoms share, the larger the atoms are, the larger the dipole or moment. So if you look at the change in electronegativity, the dipole moment, all right, 0, this is the dipole moment multiplying the charge. We use the dipole moment to calculate the percent ionic character. What is percent ionic character. You know, in ionic bond, there is total transfer of electron from one element to the other, from a metal to another. Metal takes a complete transfer. But even though in covalent bond, all right, polar covalent bond, there is transfer of electron, but not 100%. This is what is meant by percent ionic character. It's the percent of the bonds measured dipole moment compared to what if they were completely transferred. Remember the ionic bond, there's complete transfer. There's a way to calculate the percent ionic character, right? He's the percent ionic. I will not ask you to reproduce this, but it's just giving you the percent ionic character, 75%, 100%. There's no transfer for atoms with the same, such as hydrogen gas. How do you determine the percent ionic character in HCl? It's liquid. With a pond length of 127 picometers. This is picometers. This is 127 picometers. Remember, 1 picometer equals 1 times 10 raised to negative 12 meters. We need to change the bond length from picometers to meters because dipole moment is the charge times R, and R is the bond length. And in this case, a dipole moment of 1.8 or 1.08 d pi. This d pi is the unit for dipole moment. Q is the charge, and this is the charge, and the amount of charge is 1.6 times 10 raised to negative 19 coulombs. So if we plug in the two, is going to be the charge 1.6 times 10 raised to negative 19, all right, times the radius, 127 times 10 raised to negative 12 meters. So if we plug in this will be the charge for 2.03. Check with your calculator, times 10 raised to 20 negative 29 coulombs times meter. Coulombs times meter. This is the charge in coulombs, and meters unit for the radius. If we change this to divide, convert to the units for dipole moment, and this is the conversion factor. 1 divide equals to 3.34 times 10 raised to negative 34. Or 34 coulombs times meter. When I include that in the calculation, times 10 raised to negative, I think this is starting. Make sure that we have that d pi. All right, the units. This is d pi. So if we plug in that, it's going to be, all right, it's going to be, this is negative 30 here, this is 0. So if we convert that, this will be 6.03 times 10 raised to negative 29 coulombs times meter times our conversion factor. 1 d pi equals 3.34 times 10 raised to negative 30 coulombs times meter, so that coulombs will go with the coulombs, meter will go with meter, and the value here is 6.07 dBi for this problem. This is if was. Now, to calculate percent ionic character, therefore, percent ionic character is given by measured, measured dipole moment over dipole moment if the electrons. This is over dipole moment if the electrons were completely and this is times 100%. So we plug in that. This is the same as 1.8 over 6.07 times 100%. This is 17.7%. Remember, the question here is an estimate without doing detailed calculation. Identify the best estimate for its percent ionic character. It cannot be 5. If you look at 17, it's way off 5%. The closest is 15, 15, 17. If you look at 50, 80. So C, D, and A are wrong. The best estimate is B. Take home message from here. You should be able to calculate the dipole moment using the equation here. Q equals to our dipole moment is given by Q, which is the charge. You'll see this. You'll be given the constant. The point length, please remember 1 picometer equals 1 times 10 raised to negative 12, or 1 meter equals 1 times 10 raised to 12 picometers, whichever way, so that you change the radius. So correct answer is C for this case. So moving forward, last in part P, let's look at the in 10.7 how to draw the Lewis structure for molecules or polyatomic ion. These are the rules you need to remember. Write the skeleton, all right? But I'll start with the rule number 2. Calculate the total number of valence electron. When you say total number of valence electron, you have to count. Let's say if I have ICl, total valence electrons, total valence electron is I equals to 7, Cl equals to 7, and we have 14 valence electrons. That's how to calculate the total number of valence electrons, and then you distribute around the atom in such a way that the octet rule is obeyed. If an atom lacks an octet, you can either form a double bond, triple bond as necessary. If you look at this, it's just like mass you have to do, or you have to practice. You don't read it. Like if I read these rules here, it won't help me unless I practice how to write the Lewis structure for a molecule or polyatomic ion. We will look at an example here on how to draw the Lewis structure. As I said, the first is to count. We're going to use phosphorus trichloride. to illustrate how to draw the Lewis structure. So first rule is to find the total number of valence electrons by looking at the periodic table. Phosphorus is in group 5, and then chlorine is in group 7 times 2. We have 26 valence electrons. Rule number 1, total number of valence electrons. If an anion that is negatively charged or positively charged, you have to add an electron. If it is a cation, you subtract. Let's say if it is a sulfate or sulfate with an overall charge of -2, sulfur is in group 6, oxygen is in group 6, so this is going to be 6 times 4 equals to 24. And then if we add, this will give us 30. But since we have an overall charge of -2 here, we will add +2. This is what these valence electrons. This what this bullet point means, that add 1 electron for each negative. We have an overall charge of -2. That's what we have, +2 here. If it is a cation, for example, for cation NH4 positive, this nitrogen is in group 5, hydrogen is in 1 times 4. Then when we add, this will give us 9 valence electron, but there is an overall charge here. We subtract -1, we have 8 valence electrons. Remember, for positive, for cation, you subtract 1 electron for each positive. We have only 1 positive here, so we subtract 1. This is when counting the total number of valence electrons. Know how to handle cations, positively charged, and anion, negatively charged. In our case here, this is a neutral molecule. We do not need to add anything. We have 26 valence electrons. Now we need to draw the skeleton. I don't want you to just say this is connected to Cl, 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 Cl. No, this is wrong. You need to draw the skeleton with the least electronegative on the periodic table being at the center. And you do the math. Rule number 2, you subtract the bonding electrons. Here there is a bond, there is a bond, there is a bond. We subtract 6 electrons for bonding electrons. So here we say 26 minus 6. These are the bonding electrons from these 3 lines. There are 2 electrons, there are 2 electrons, there are 2 electrons. So once you are 20 remaining, all right, 20 electrons remaining, what do we do with this? First priority in satisfying the octet rule, whatever is left, whatever is remaining, we satisfy the octet rule on the external atom. These are considered as external atoms. The way they are right now, we have only 2 electrons. It needs 6 more to satisfy the octet rule. So we distribute this from the remaining 6, 6, 6. So 20 minus 18 remain to whatever is left, just put it on the central atom. Once you satisfy the octet rule, you put it on the central atom, and the 2 electrons now are on phosphorus, and nothing remains. You have to do the inspection if there is a need to form a double bond or triple bond to satisfy the octet rule, but we do not need, because here we have 2 phosphorus satisfy the octet rule, and each chlorine satisfy the octet rule. So multiple bonds is unnecessary here. If it was necessary, that means if one of them was not really satisfying the octet rule, such as in hydrogen cyanide, we got to make a double bond, because hydrogen as 2 electrons, the dual. We don't worry about hydrogen. But if you look at carbon, 1, 2, 4, so it needs 4 more to satisfy the rule. So if you look at this, you stay lone pairs on the external atom to form a triple bond in nitrogen cyanide. That's how you generate the double bond, triple bond. Simple question in exam, the ion, just the molecule. Here, ICl has dash valence electron, shouldn't have been ion. This is not an ion, it's just a molecule. Iodide and chlorine, the correct answer here is 14. Iodine is input 7, chlorine is input 7, 7 valence electrons, 14. We need to be able to calculate the total valence electron. Now, draw the Lewis structure for carbonate ion. So if I have this as an example, let's see. CO3 to negative. Carbon, this is 4. Oxygen is 3 times 6 is 6. So this is 18. Give us 22. Because there's an overall charge here, we need to add plus 2 electrons. We have 24 valence electrons. Rule number 1. Count the total number of valence electrons. Here is valence electrons. Number 2, draw the skeleton. So if I draw the skeleton of the molecule, carbon bonded to 3 oxygen. Subtract the bonding, all right? Subtract the bonding electrons, so it's going to be 32. You see the total number, oh no, 24. 32, 24, 24 minus the bonding. We have 1, 2, 3. We have used 6, remain 18. Remain 18. So if we keep it to each oxygen, minus 18, this is 0. But if you look at carbon, it does not satisfy the octet rule. So in order to do that, we can have a double bond here, carbon, oxygen, oxygen. This has 6 electrons each, but this will have 4. We have used the 2 here to make a double bond here. We remain with 4. We have that. Sometimes, and then we have put in parentheses the overall charge of -2, overall charge of -2. Please practice more using or look at problem 53, 55, 56 on page 4, 39 in the text on how to draw the Lewis structure. This marks the end of part B of chapter 10. I'll see you again in part C.